today we can see about coefficient quantization error. Okay, so today here we are having two concepts. One is the quantization. First of all, let's see what is quantization. What is quantization? So quantization, it is nothing but a process of mapping continuous infinite value to a smaller set of discrete value. So, so if you are having a continuous infinite value, so we are mapping this continuous infinite value to a smaller set of discrete value. This process is called as quantization. So quantization is the process of mapping continuous infinite value to a smaller set of discrete value. So as all of us know that this quantization process is done by two methods. One is the truncation and another one is the rounding. So truncation is nothing but truncating and discard the remaining bits, and rounding is rounding to the nearest value. So based on these two methods, the quantization will be performed. Now, what is coefficient? What is coefficient? We all know that coefficient. So the IAR filter is characterized by a system function h of z equal to summation k equal to 0 to m bk z power minus k by 1 plus summation k equal to 1 to n ak into z power minus k. So where this bk and this ak are the coefficients. So this bk is the coefficient of this z power minus k, and ak are the coefficients of z power minus k. So bk and ak are the coefficients for this IAR system function. Then what do you mean by coefficient quantization error? So coefficient, now we know about coefficient and quantization. So what do you mean by coefficient quantization error? So if a quantization, this quantization is applied to the coefficient, the frequency response of the resulting filter may differ from the desired frequency. Okay, so quantization means truncation and rounding we are performing. So when this continuous values is mapping to a small set of discrete values, this is called as coefficient quantization error. Okay, so let us solve one problem. Okay, so this is problem given. Consider a second order IAR filter with h of z equal to 1 divided by 1 minus 0.9 z inverse plus 0.225 z power minus 2. Find the effect on quantization on pole locations. Take b equal to 3 bits. So given a system function, IAR system function, 1 divided by 1 minus 0.9 z. So from here, what are the coefficients? This 0.9 and 0.225 are the coefficients. This 0.95 is the coefficient of z inverse and 0.225 are the coefficients of z power minus 2. Okay, so and also it is asked to quantized to bit 3 bits, b equal to 3 bits. Okay, so let's solve this problem. So the given solution is, system function is h of z equal to 1 divided by 1 minus 0.9 z inverse plus 0.225 z power minus 2. So first of all, we need to convert the coefficients to binary. Okay, so let's consider the first coefficients 0.95. Okay, this is point, take this as 0.95. Okay, so we are going to convert 0.95 we are going to convert this to binary. So how will you convert this 0.95 to binary? So to convert this binary, we want to multiply 0.95 with 2. So the answer is 1.9. So this one comes here. Okay, so again this 0.9 we are taking here, 0.9 again multiplied by 2, so the answer is 1.8. So once 1 come here, so the binary value is 1, and this 0.8, 0.8 into 2, so the answer is 1.6. so this 1 again 0.6 into 2, that is 1.2. so this 1 comes here, so 0.2 into 2, that is 0.40, and so on. So this will go like this. So the binary value of this 0.95 is point, this one 1 1 1 1 1 0 1 1 1 1 0. Okay, so what we did was, now we convert this decimal to binary, and in the problem it is asked to quantize to 3 bits. Okay, so what we are going to do is, we are going to consider only 3 bit, 1 2 3. We are truncating and discarding the remaining bits, so we are going to consider only 3 bits. So truncate to 3 bits. Okay, truncation is nothing but the quantization. We are going to apply the quantization. So truncate to 3 bits means we are only having 0.111. Only we are having the 3 bits. Okay, so now again this binary value we need to convert to decimal. How we will convert to decimal? So we need to convert this binary to decimal value. Okay, so 0.111. Okay, so this we need to, this 0.111 we want to convert into decimal. So 1 into 2 power minus 1 plus 1 into 2 power minus 2, then next one plus 1 into 2 power minus 3. Okay, so how will you find this one? 1 into 1 by 2, that is 0.5 plus 1 into 2 power 2 square is 4, so 1 into 1 by 4, that is 0.25. Similarly this one is 0.125, so this is 0.875. Okay, so converting this binary to decimal, we will get 0.875. Okay, so this is the effect of coefficient. Just to check this, so what we applied means, we applied the coefficient of Z inverse, we performed the truncation, quantization, so the error occur. Okay, so some effects will be occurred when performing the quantization. So this is called as the coefficient quantization error. Okay, so this is about the coefficient of Z inverse. Similarly, what we want to do is, we want to perform the coefficient of the second value, that is 0.225, the coefficient of Z power minus 2. So coefficient of Z power minus 2, that is 0.225. Initially we need to convert this to binary. The same procedure we are following here. 0.225 into 2, that is 0.45. This 0 come here, so value is 0. So again this 0.45 into 2, that is 0.9. So this 0 comes here, 0. This 0.9 comes here, 0.9 into 2, 1.8. This 1 comes here, 1. 0.8 comes here, 0.8 into 2, that is 1.6, 1, and so on. Okay, so converting to the binary, we will get 0.00111 and so on. So in this problem, we are truncating this value to 3 bits. So we are considering only 3 bits. Okay, so when truncate to 3 bits, this value will be 0.001. Now again what we want to do, we want to convert this to decimal value. How will you convert this into decimal? So the first digit 0 into 2 power minus 1 plus the second value 0 into 2 power minus 2 plus the third value plus 1 into 2 power minus 3. 0 into any number, that is 0 plus 1 divided by 8, that is 0.125. So while converting this binary to decimal, we will get 0.125. Okay, so here also while we try applying the quantization, this 0.225 we will get 0.125. Some errors will be occurred when performing the quantization. This is called as the coefficient quantization error. So now we are rewriting the expression. So we know that the given system, IAR system function is, what is the system function given? H of z equal to 1 divided by 1 minus 0.95 z inverse plus 0.225 z power minus 2. This is the given system function. After applying the quantization to the coefficients, what we get? 1 divided by 1 minus, so we applied quantization to this coefficient, that is 0.95. What we got? That is 0.875. So this is 0.875 z inverse. Similarly, the coefficient of 0.225, we applied quantization here and we got 0.125 into z power minus 2. So when applying the quantization to the coefficients 0.95, errors will be occurring here due to the quantization. So this effect is called as the coefficient quantization error.